So I figured I would make the best possible argument for these folks. And that's exactly what the argument would be, is that since this isn't inertial and it's actually in a rotating frame, that this would actually create a pseudo-gravitational field. And since this would be in the vicinity of where the gravitational field is created, and down here on Earth would be much farther away from that gravitational field, then this would be considered the lower clock that would run slower as a consequence of gravity, and this would be considered the higher clock that would run faster as a consequence of being farther away from that gravity. And because the Colorado clock would be running faster as a consequence of the pseudo-gravity, that would be the thing that would undo the problem of the 7,000 nanoseconds that was imparted as running slower from the perspective of the Earth. So interestingly, two different phenomenon are actually proposed to create an equal but opposite effect so that we can actually get a two-way syncing system. There's plenty of problems with that, however. The first problem is that in a case like that, we'd have a hard time using this in its entirety because, like I said, this isn't really a true rotating frame. It's a satellite, and everything else, including the surface of the Earth, would not be in the same frame of rotation that the satellite is in. And the other big thing is that the surface of the Earth clocks, whether we're talking about the ground control stations or the GPS receivers inside of automobiles, they're actually not in dead center, in the center of the Earth, which would be the center of the circle here. We could look at this circle and say, an overhead view, we'd have the satellite going here, and then the dead center of the circle would be the center of that circle for this rotating frame. But in this case, we're outside of the circle, technically about 25% outside of the circle. So we've actually moved off of the center, and it's my argument that this entire thing wouldn't apply. Now, the other thing, too, is part of my argument was, well, if we can take Galileo to the extreme and say that, hey, I'm the one who's not moving and the entire universe is actually moving under my feet, and it's okay for me to say that, then what can we say about anything in orbit? For example, if we, instead of talking about a satellite orbiting the Earth, we could talk about the planet Uranus orbiting the Sun. And Uranus has an interesting orbit because it actually, unlike the moon, it doesn't have the same side facing the thing that it's orbiting all the time, but yet it's not rotating excessively in any one direction or the other. So it would be kind of like envisioning taking a compass needle on a tabletop and kind of having the compass needle orbit the center of the tabletop. It'll be going in a circular path around a particular center, but the needle will always be pointing in one direction. If you were to put a tiny camera on the end of that compass needle that would be facing north the entire time, and you rotated it around that center, whether it's a planet or whatever, then you could make the argument like Galileo made for linear motion, that it's just as valid to consider that center object rotating around that compass needle, because in the field of view of the camera on that needle, you would actually see that centerpiece in a state of rotation. So it's hard to believe that if you were to suddenly go from being the planet Uranus to just tidal locking like the moon and then staring straight at your center object the entire time and not rotating, that would drastically change the time dilation between those two objects. So that was kind of my thinking. It has kind of progressed, and I've got a few other criticisms as to why this is not a good idea to use. And then I've got another thing that will kind of talk about another form of relative motion here, even if you don't like the planet Uranus example. The problem with this gravitational potential used in this rotating frame is that, and I pointed this out on an earlier slide, Einstein made an assumption that I don't think is true. And the assumption that he made is that once he deemed all gravitational potentials basically having the same relationship with time dilation, he wasn't careful about how the circumstances changed and how the cause and effect was different. And the reason why that's extremely important here is that in the very first example, we were talking about an elevator, we were talking about linear acceleration, and the very act of the acceleration was what induced the signal shifts, and the signal frequency shifts in itself was synonymous with one clock running faster and the other clock running slower. As erroneous as I think the twin paradox solution is from the point of view of Einstein, at least in one direction, we've got a correct signal shift. I had said that in the turnaround phase, the problem there is that we have blue shifting from the view of both parties, where in order for it to maintain true to the principle of equivalence, it should really be something that's blue shifting in one direction and red shifting in another, since you're producing equal but opposite time dilation effects. One clock is speeding up, the other one is slowing down, and that was actually necessary to undo the twin paradox and resolve what we would see when that clock returns home. But having said that, we got blue shifting in both parties instead of blue shifting on one and red shifting on the other. So that, in my opinion, was at least half right. The problem with this is when you're in a rotating frame, the signals, and they could even be generated as pulses. Feynman, in his lecture on physics, actually talks about flashes of light 1 second apart. So we wouldn't even necessarily have to talk about light frequencies stretching from red to blue or vice versa. We could actually send pulses of light out from the center in all directions at the same time. And if those pulses of light were 1 second apart, this is actually in a state of perpendicular motion. It's not moving away from the light, it's not moving toward the light, and as a rotating frame, it's not moving in any one direction or another. So unfortunately, the relationship between these two clocks, and this would be when we're close in here, we are going to get a little distance change, which I'll address in a second. But even if we were going from the center to the satellite, the motion of the satellite and its relationship with the center clock is not going to induce any signal shift. It's not going to induce any red shift. It's not going to induce any blue shift as a consequence of the motion of itself. That's important. There are a lot that argue that, well, of course, the gravitational situation of the satellite, the inducing of the gravity itself will actually cause the clock to speed up and slow down. But if we go back to the original example, what it was based on, it was based on the signal shifting. And it was a very neat cause and effect relationship between the two. Now we're in an example where we have a simulated gravity, but we don't have the gravity imparting a necessary signal shift to slow down the clocks. That's huge. And like I said, the problem with that is we will not get that time change that the critics would suggest with that. So then we would have no choice to, if we still wanted to salvage gravity, or simulated gravity in this case, as a source of altering the clocks between the two clocks, then it would be a local effect, and it wouldn't be something that would be dictated by distance between the two. Problem is if we say that the gravitational effect on time is local, it's because of the actual gravity itself and some sort of material effect on that clock because it's experiencing gravity, well then now we have to re-examine its inconsistency with the original 1911, because in our elevator example, the G values were actually the same on the floor and the ceiling of the elevator.